and thank you everyone for having me here. I really had enough of the Zoom presentations. I wish next year we can do it in person and won't have all these technical problems, and also would be wonderful to see people faces. My name is Elad Hazan. I'm from Princeton. I'll talk about joint work with Shini Chen and Edgar Minasian, who are my students, and Jason Lee, who is a professor in Princeton and the researcher in the area of deep learning. And this talk is about online and agnostic deep learning. I will say a little bit about how I became interested in this topic. I myself am not a deep learning expert, although I kind of learned to like the topic after collaborating with Nadav that just talked. Recently, we've been working on control, and control is a field of engineering and science that deals with operating mechanical devices and achieving desired functionality. An example of such that became very interesting to us in the COVID pandemic is that of medical ventilation. In this problem, the goal is to allow air or oxygen into a patient's lungs in such a way to track a waveform of healthy breathing. Obviously, this is a problem or an online problem with various variables that are unknown ahead of time, because the patient lungs, airways, obstructions, and so on differ from person to person. In this problem, the goal is to track the waveform that the clinician prescribes. I hope you can see my mouse here on the screen. Is this visible, the mouse? Yeah? Okay, good. So this dashed black line here is, for example, a waveform that a clinician prescribes to a patient that we want. This is the volume of air that we would like to have in the target patient lungs. And we have been working on a variety of methods, both classical and the new approach is based on deep neural network controllers, and they significantly outperformed classical methods. And this investigation started as an attempt to understand why. We all know deep learning works very well, but to give some kind of theoretical foundations to this success of deep learning, not only in the classical scenario of supervised learning, but also in online learning and reinforcement learning or control. So deep learning theory contains numerous approaches, hypotheses, conjectures, and so on. I think it is safe to say that there is more unknowns than knowns. And there are numerous fields of study that came to being because of this new science, some of which is particularly dear to my heart, such as adaptive gradient methods in optimization, something I've been working on for a long time, but there are, of course, many other fields of study that are listed here. I think in terms of the theoretical success, the main theory or the main theoretical framework that gives provable bounds for deep neural networks in supervised learning is called neural tangent kernel theory. And I've listed some of the references here. It's not all of them, but this is some of the seminal papers that gave rise to this theory. And this theory characterizes what happens to overparametrized neural networks. This means there are more parameters than data points. When we train it using gradient descent, and it can show that indeed zero training error was reached, there are some positive results on generalization error, and so on. However, the current theory is applicable to supervised learning, batch training model, stateless learning, and for the most part, and this can be seen from, I think, other talks in this session, people only look at gradient descent or stochastic gradient descent and try to analyze the dynamics of what happens there. What I would like to see is an online learning, or what we would like for this, for applying deep learning to control, is an application to online learning, agnostic, meaning that we are able to capture noise or adversarial or adapt to the environment on the fly, and in general, a much more general theory that can be applicable to more generic domains. So the result that I will describe is a reduction that takes a deep neural net. The deep neural net can be arbitrary depth. We study ReLU activations, even though I think that what I describe is robust to the activations, can be any nonlinear activations. We only look at fully connected nets for now, but again, I believe the result is robust. And what we would like to do is use the existing theory of supervised learning or neural tangent kernel theory in an online learning manner. So we can feed the neural net an adversarial sequence of cost functions, convex cost functions, and obtain provable regret bounds. Regret is a metric that measures the overall loss compared to the best loss in hindsight by the best net, and it is a more general notion than statistical generalization. Statistical learning theory, it implies that, and thus many times harder to achieve, and many times not as good of a rates and so on. Nevertheless, this is the applicable metric for online learning. So this is going to be a reduction. The reduction can take any online convex optimization algorithm. It's not restricted to stochastic gradient descent. It can be mirror descent or Newton method, or any kind of optimization algorithm that we know from mathematical optimization theory. And in that case, this is sort of you can think of it as sort of an envelope wrapping the existing theory for deep learning, supervised deep learning, by something that is a bit more generic and can help explain other phenomena. Now, when we talk about regret, this is very different from supervised learning. We need to quantify what we mean, because regret is inherently a relative metric. It says like my performance is as good as something. This is different from supervised learning when you have a training set and you say, okay, I would like my entire training set to be classified correctly, and if my capacity is bounded, I get some generalization error bound. So you have a clear metric over the training set, what you would like to happen. You would like to have zero error. But in online learning, it's impossible, because you cannot have zero error over any sequence. This is impossible due to Kolmogorov complexity considerations, right? You cannot predict an arbitrary sequence. You must compete with something. And for that reason, we need to formally characterize what do we mean by expressiveness of a net, because it is very easy to say, oh, we have regret compared to the best net in hindsight. But the best net from which class? From the initialization, and we don't change it, and we don't allow the net to change at all. Okay, then of course you have regret, but compared to a very small class, that is not expressive at all. You do want to capture something about the expressiveness of the model, and here it is useful to recall classical notions from learning theory. For example, in binary learning, it's not what our target. Our target is real valued learning. But from binary learning, we have something called the VC dimension that characterizes an upper bound on the sample complexity. And that, if you recall, says, okay, what is the largest set of cardinality of a set that can be shattered? Namely, it can be classified in all possible ways. Whatever that cardinality is, captures the sample complexity for learning a concept. But it does not capture the expressivity of the hypothesis class. For that, we need to look at a different notion. So let me call the interpolation dimension the largest such set, cardinality of a set, such that all sets of this class are shattered. If you can shatter, we can classify correctly, such as in this picture here. We use linear classifiers to give all possible labelings of red and blue to the 3 dots. If any set can be shattered in every way, this is one notion of expressivity that we could use. Okay. What about real valued function? You can have a very similar definition. You can say, okay, a hypothesis class has interpolation dimension k if for every set of k points, we can assign any real valued label to it. So here's the main theorem that we can prove. For any size of deep net and any architecture activations and so on, there is an efficient online algorithm that can do the following. And we need 2 things here. One of them is expressive, otherwise the whole thing is vacuous. So the interpolation dimension can grow with the size of the net by some polynomial. And second of all, the regret is also bounded by sublinear function of the number of iterations and the size of the network. This is the main theory. Due to time constraint, I will not go over the exact parameterization of the complexity. But I do want to say, I do have time to say why it works. So actually, the reason why it works relates to known results from supervised deep learning. First of all, there is a polynomial expressivity that we need to prove that says that a neural net with m nodes has interpolation dimension that grows with m, some k that grows with m. And second of all, the second thing we prove is that these are nearly convex. So near initialization, if you don't move far away, the Hessian is lower bounded by some small quantity that goes smaller and smaller as the number of nodes increases. And this means it's almost convex, and you can use convex optimization techniques. Let me explain the first part, and I'm only doing intuition now. Why is a neural net expressive if it's overparametrized? If the number of parameters is more than the data, why is it expressive? What we can do, we can, near initialization, we can write the linearization. This is neural tangent kernel theory. The linearization of the deep net at the current point, theta 0, that's the parameterization, plus something small, which is the second order term. Now, if we want to interpolate k points, that amounts to solving a linear system, and the number of points k going to be smaller than the number of parameters in the network. This means we have an underdetermined system as long as the number of parameters is bigger than the number of points we're trying to express. And this has been made formal by papers here for some types of inputs, and by, I'm not listing the whole literature, but this is sort of a known phenomenon that happens for neural nets, or actually any machine with a small second order term. So that's intuition number one. And intuition number two, why is the net nearly convex near initialization? And the idea is the initialization we take is a standard initialization in the literature, which you take the weights to be plus minus 1 over root size of the net. Near initialization, if we linearize the net, or everything that goes below the first layer can be approximated by some kind of a fixed constant. And the only remaining important part is the top layer, where each component is scaled by this 1 over root size of the net. So that bounds every component by our initialization constant, which is 1 over root m, so that gives a spectral norm bound on the Hessian. I should note that when we have here, we have m width of m. So having width of m with 1 over root m initialization still allows you to express a constant output just because the sum of m random variables plus minus 1 is roughly root of the number of variables you sum up. So these are the two main intuitions. And how do we cap this? So the conclusion is the following. Given a deep net, we know it is nearly convex. So this means you can add some small strong convexity component to whatever loss function that someone throws at you. It becomes convex. And now we can use machinery that we know already from online learning to achieve regret bounds, any machinery. So this allows you the flexibility of doing not only SGD or gradient descent, but mirror descent, multiplicative weights, follow the perturb leader, any convex algorithm, and kind of decouples the optimization from the machinery, which is a property that I like. At least for my understanding, it's much clearer to work this way, where you have a separation between the two things. So the near convexity property is used here to get a regret bound with the standard technology from online learning. And the second issue is that this is not a vacuous statement, because we can prove that these machines are expressive. Their interpolation dimension grows with the width of the network. So this is how the entire, I hope I described the online learning result. How does it tie in back into the original problem of control I wanted to attack? So just to recap, the conclusion is that deep nets have interpolation dimension that grows with their size, plus we can get a regret bound due to the near convex structure. Tying it back to control, in a control problem, we not only have a sequence of loss functions, but we also have a state in the environment. You can think of it as the amount of air in the patient lungs. A metric that has been proposed to use in control is regret compared to the best policy, best algorithm to control the machine. And using the framework of online learning, we can map a control problem to a sequence of online learning functions and apply the machinery I described to prove regret bounds for a convex policy class of controllers, which are deep neural nets. So that is how it ties back into the control. I know this is brief, but please check out our paper for more details. And at this point, I think I'm nearly over time, so I'd like to thank my collaborators, Shini, Edgar, and Jason, and thank you for listening, and happy to take any.
Thank you, Elad. Is there some, would you say that there is some practical conclusion about the advantages that other optimization approaches could have in deep learning from the bounds you obtain?
That is really a fantastic question, and I want to remark it's not planted. This is something that came. It's a really good question. We know from, I think that's one of the advantages of this result, because we allow any optimization algorithm and so on. So we know from online learning that when you have bounds on the diameter and the gradients of the loss functions, different regularizations are important. For example, if you have a sparse input and an L-infinity bound on the diameter, then you want to use some sparse method like lasso or L1 regularization or multiplicative weight. And if you have a dense input, you might as well use gradient descent. So the same intuition applies now here. If your weights are bounded in Euclidean norm and you expect dense inputs, you should use gradient descent. If you have your weights are bounded in infinity norm and you have sparse input, you should use some multiplicative weight based algorithm, and both of them will converge to the global optimum, but we will have the advantages that we know already from optimization theory on the rates that these methods will deliver.